Thank you, Shivam. Thank you. Okay. Yeah. So a direct consequence of this fact is whenever you raise this to any multiple of p minus 1, you will again get 1 only. By this thing, I simply mean mod p. So now that we have seen this, that any multiple of p minus 1 also gives you the answer as 1. The next question that comes to mind is that if a raised to the power n is congruent to 1 modulo p, does that imply that n is divisible by p minus 1?
No.
Okay, I see. Anyone else? Oh, Shivam, can you give me an example of why that's just not true?
Okay, wait a minute. Let me think one.
Sure. Anyone who gets an example, I'll give you like 20 seconds to think of it. If you get an example, tell me.
P plus 1 power anything would be congruent to 1 mod p.
Yes, that is indeed correct. So one example which is quite obvious is p plus 1 to the power anything is always congruent to 1 modulo p. Similarly, minus 1 raised to the power any even number is also congruent to 1 mod p. These are like some sort of a trivial example, if I must say so, because what you get is you're not really getting any new information. Like 1 and minus 1 will always be like lie in those two. You're not getting any new information. So like one small such thing you can get is 2 raised to the power 3 is congruent to 1 modulo 7. Yeah, that is true. So this gives us an example, and we can clearly say that 3 is not divisible by 6. Yeah. So what this motivates us to do is define we define something called the order of A modulo P. Simply what this means is the smallest A such that, okay, no, smallest n such that A raised to the power n congruent to 1 mod P. Is the definition of what an order is clear to everyone?
Does P need to be prime?
Yes, P needs to be a prime. The point is, whenever P is not a prime, most of the times what you can do is like do like break it into its prime factors and then use Chinese remainder theorem to go back. And why you need P to be a prime is take for example 3. 3 raised to the power n is never congruent to 1 modulo 15. Can someone prove this statement? Like 3 raised to the power n is never congruent to 1 modulo 15.
15 is congruent to 0 mod 3, but 3 power n minus 1 is congruent to, it's not congruent to 0 mod 3. So,
No, I don't get that. Dundee order. No, that is not correct, right? Well, I mean, yes, 15 is 0 mod 3. But how does that mean that 3 to the n is not 1 mod 13?
if 3 power n minus 1 is divisible by 15, then 3 power n minus 1 should be divisible by 3.
Yes, that is the correct. Oh, right. Okay, you meant it that way. Yes, that is indeed correct. Sorry, I did not understand that. So, did everyone get what Anirudh just said?
Yes.
Nice. Just a second. Someone wants a different problem. I'll give them that. Let's see. Problem on orders, right? Okay. Yeah, this works. Why can't I print screen? Okay, I can't print screen. This is so annoying. Wait, is this? Oh, it is indeed visible. Nice. So yeah, whatever that was, just look at this problem. I'll just remove some extra stuff. This is the extra buffer problem in case someone has already done the one before. This is the problem, buffer problem for the ones who have done the other problem before. Okay. Yes. Also, Shivam, does that answer why that is not the case? Like why P needs to be a prime?
Yes.
Good.
Can't we do something with Euler's?
How? And about what?
Since we have phi of n, if n is not a prime, so I think
Yeah, that is true. But what you will need again there, see, when you are doing that, what you can simply do is reduce it modulo like p powers, right? Like suppose that your n is equal to some p1 alpha 1, p2 alpha 2, so until pn pk alpha k. Okay, suppose that this statement holds. So instead of looking at some a raised to the power t congruent to 1, just simply look at a raised to the power t1 congruent to 1 modulo p1 alpha 1. So on a raised to the power tk congruent to 1 p1 pk alpha k. And then you can then what you can do is CRT to get the main n back. Did that make sense?
yes.
Okay, nice. Okay, so the first result will prove today. Okay, also order of a mod p is very, 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 very clunky to write. So this is abbreviated as order of a modulo p. This is the abbreviation for this statement. Okay, so lemma. This is the first thing we'll prove today. A raised to the power n congruent to 1 modulo p is equivalent to saying order of a modulo p divides n minus 1. Sorry, not n minus 1, simply n. Yeah. So think about this for like 2-3 minutes. Isn't it r equal to 2k? Oh, r equal to 2k will be forced by that, but it's not given initially. It will be forced, but it won't be given initially. Either way, whoever has like any idea or anything about this problem, just feel free to unmute and say.
Like in this lemma, we can do that like a raised to the power d is congruent to 1 mod p, where
Okay.
d is the smallest positive integer satisfying this condition.
So
So
the order.
yes. So so case 1 will be n equal to d if it
Okay.
assume, and if we assume, and in this condition d
Hmm.
p should not divide d.
Should not divide D. Wait, what should not divide D?
D should not divide p.
Uh, okay, sure. Like
So
the only factors of P are 1 and P itself. So D not dividing P is kind of a weird condition, right? I mean, if some K divides P, that implies K is either 1 or P. So yeah,
like the only condition left is n equal to d multiplied by k plus r plus r, and the r should only be like 0.
yeah, that is correct. Also, Anirudh, yes, your answer is also. So people, we proceed with the proof now. Observe that this is an if and only if condition. So we want to state two proofs. We want to like prove two things here. We will proceed with the first direction, which is like if order of P modulo A divides n, that implies A raised to the power n is congruent to 1 modulo P. So this is not the hard part to prove. Suppose n is equal to k into the order of P mod A, that implies A raised to the power n is congruent to A raised to the power k into order of P modulo A, which is congruent to A raised to the power order P mod A whole raised to the power k, congruent to 1 modulo P. So was the first part clear to everyone? It isn't a hard one. Was that clear? I suppose that's a yes. Also, Ayush, here I think you solved the other problem. So here is another buffer problem. Okay, that is horribly written. Why can't I take a screenshot? That's one on. Hmm. Okay, Ayush, try IMO shortlist 2012 and 6. IMO shortlist 2012 and 6. It's a problem based on ideas like order only. So try that. Okay. As for the other condition, that is also quite straightforward. For the sake of contradiction, assume that order of P mod A does not divide n. Then by the Euclidean algorithm, I can write n is equal to k times of order P mod A plus r, where this r is upper bounded by order P mod A and is at least 0. So we would get A raised to the power n congruent to A raised to the power k times the order P mod A plus r congruent to 1 times A raised to the power of r, and this is congruent to 1. So we get a new r which is congruent to 1. But observe that this statement implies that r is less than the order of P, and r is also A raised to the power r is also 1 mod P. this contradicts the definition of R. So, sorry, the definition of order of A mod P. So this is a contradiction. Was that clear, people?
Yes.
Yes, it was clear.
Yes. Also others, like, am I making sense? I will take that as a yes, though it will be nice if you can speak up. Either way, let's just go over some simple problems of orders. Let me recall the problem. Yeah, this works. So, problem. Find all n belonging to the natural numbers such that n divides 2 to the n minus 1. Think on this for 3-4 minutes and then I'll get back. Also, feel free to like say any ideas you get, anything. Also, have most of you seen this problem already? If most of you have seen this problem already, we can skip this and like go to harder problems. Yes, this is from Mont. I agree, this is from Mont. Maybe I have also seen this, yes. Okay, I suppose most of you have seen the problem. So I will instead switch to a better problem. Have most of you also seen this one? N divides 2 raised to the power n minus 1. Was it minus 1 or plus 1? Plus 1, I think. Yeah. Have most of you seen this problem as well? Seen but didn't solve. Okay. Nice. So let's just solve this problem. Think on this for 2-3 minutes. Give me any ideas you get. Oh wait, the new people. Shivam, Bratjit, and all the new people. Have you seen the first problem?
Yes, but didn't solve.
Oh, okay. So, sure. Everyone who has seen that problem, try this one. We'll do this in like 5 minutes and then come to this problem. What did I miss? Kushagra, if I'm not spelling the name wrong. We have defined what an order is. We have defined what an order is. Okay, that was so long. We have defined what an order is. There were many buffer problems given. And then we proved our first lemma, which is if a to the n is 1 mod b, then order a divides n. And now we are trying some problems. Most of the people have done this problem, like solved before. So whoever has solved this, try this problem. Otherwise do it. Anyways, Shivam, Bratijit, and like every people. Oh, Advik is also here. Hello, Advik. So yeah, you people. Any ideas?
In the first problem, we can say that the order of 2 in n divides n.
N divides n. Okay, no, Arsh, remember we defined orders only for primes. Okay, we haven't yet defined orders for
Oh, okay, right. Sorry.
yes, because the main issue with that is like, okay, that isn't really an issue here, but okay, I agree. So, but one thing in number theory is that whenever you have an n, try to reduce it to a prime because primes are just much better to deal with. okay, it's in general much better to deal with if you
Okay.
have that stuff.
Got
Oh wait, before this, okay, sorry, I made a mistake. Let's just prove another lemma. Lemma. If P is a prime, then order of A modulo P divides P minus 1. Can anyone tell me why this is? This is a direct corollary of this statement.
Through formats.
Yes, precisely. So Fermat's little theorem tells that A to the P minus 1 is congruent to 1, and then by lemma 1 we conclude. Okay, my English is still bad. Either way. So now we have the machinery to solve the first problem. Any ideas, people?
You can take some prime dividing n, and then that prime will divide 2 raised to n minus 1.
Yes, that is correct. That is a good
Uh,
idea.
and then you take, so the order will have to divide the GCD of p minus 1 and n,
Yeah.
and
Wait,
then you
what?
can take p to be the.
Yes, that is indeed correct. So yeah. So what he's saying is that take a prime P that divides n. So we get that P divides 2 raised to the power n minus 1. Now this then implies that 2 raised to the power n is congruent to 1 modulo P. Therefore, order of A modulo P divides n. What next?
Since the order must also divide p minus 1 because of format,
Yes,
we
that
can
is correct.
conclude that the order
Order
must
of
divide
2, not
GCD
the
of
order of A, by the way.
What?
It's the order of 2, not the order of A. Every
Oh,
time.
yes. Thank you. Indeed, it is like order of 2. Thank you. Yes, so yes, Keshav, you are correct. This is the first like interesting idea we have. We observe that order of P modulo 2 divides n and order of P modulo 2 divides P minus 1 as well. These statements together imply that order of 2 modulo P divides the GCD of n and P minus 1. Is this clear to everyone? Like this thing, is this clear to everyone?
Yes.
Nice. And how do we how do we proceed with this now?
And
now you
GCD will
can
be 1.
No, the GCD might not be 1.
take p to be minimal.
Indeed. So now we observe that if I take P to be the smallest prime divisor of n, then GCD of n and P minus 1 is just 1. Why is, okay, this is a trivial statement, but why is this true? Like, anyone?
If something smaller than p is dividing n, then that's a contradiction to our assumption.
Precisely. So we get that this has to be 1 Hence, order of 2 modulo p divides 1, which in turn implies that order of p modulo 2 is 1. So that implies 2 raised to the power 1 is congruent to 1, or 1 is congruent to 0 modulo p, which is utter nonsense. Therefore, we are done. Either way, we skipped a little detail here. Can someone tell me what that is?
We didn't check one, n equal to 1.
Yes, that and one more thing. Anyone?
N equal to 2?
Yes, in some sense. We are freely using the order of 2 modulo p, but we never checked if this actually exists. Like, what happens if p is equal to 2? Then we are in an issue, right? Like, because then we will never, like, this order just won't exist then. It will not exist. It will be 0. So we need to verify that p is not equal to 2. And that isn't difficult. Like, why can 2 not divide 2n minus 1?
Because even can't divide odd.
Exactly. Yeah, that just finishes. So we get that there are no solutions, but whenever you're doing this order business and assuming that a prime p divides this guy, always check 1. Okay, check 1 and we get that it works. Yay, we have solved our first problem. Was that clear to everyone?
Yep.
Yes.
Okay, I suppose it was clear to the other people as well, but do speak up or write in chat. Yes. So let's just do the next problem. N divides 2 raised to the power n minus 1 plus 1. I suppose most people haven't seen this, right?
No, I have not.
Yes. In case anyone has also seen this problem, do the buffer problem.
I have seen this but was not able to solve.
Yeah. Okay, not being able to solve, yeah, that is more accurate. Anyone who has seen this and was not able to solve it, feel free to share your ideas.
Is it from Mont also?
What?
Is it from Mont also? This question is from Mont.
I don't really have an idea. I have solved this problem like some time ago. I just remember it. I don't know if this is from Mont or not.
Okay.
Oh, also, you people have had an NT class before, right?
Yes, yes.
Okay, good. Was this discussed in it by any chance? P divides a square plus 1 implies that P is congruent to 1 modulo 4.
This is Fermat's Christmas theorem.
It is indeed Fermat's Christmas theorem.
This wasn't discussed. I don't think this was discussed.
Wait, this wasn't discussed. Ah, that is pretty sad. Okay, so let's us. What do you want to do first? Like, do you want to assume that this lemma holds true and then prove that this problem is true? Or do you first want to prove this problem and, prove this lemma and then do the problem? Which do you people want to do?
Prove the lemma.
Yeah, the lemma isn't that hard to prove, right?
I agree, it isn't that hard to prove. Okay. Wait, how? Wait, won't you need a little bit of quadratic residues to prove this?
No, you just say a raised to 4 is congruent to 1 mod p, and then you do order stuff. And so you get 4 divides p
Ah,
minus 1.
that makes sense. That makes sense. Yes. Okay, people. So do you want to present a proof, or should I just give you the proof?
I
say
presented, but I know it.
one.
Wait, two people were speaking at once. I heard Keshav. Who else was speaking? I suppose no one. Anyways, other than Keshav, anyone who has an idea. Nothing against you. Like you're just you know this stuff before, right? So those who don't should also get a chance. Yeah.
Can you use
A square plus 1 congruent.
A square plus one congruent to what? Yes, Akshar.
1.
Oh, wait. So if a square plus 1 is congruent to 1 modulo some prime q, then that will be the same as saying that this happens. But observe that
4, mod 4.
mod 4. Okay, yeah, that is a good idea. Is that a good idea? I don't know. Oh wait, observe that a square plus 1 congruent to 1 mod 4 implies that 2 divides a. But this statement gives us no new information about this gives us no new information about that thing, p itself. Oh yes, in this problem n is just a natural number. Find all in that one. Okay, so I'll tell you people, I suppose. See, we are given that a square plus 1 is congruent to 0 modulo p. So a square is congruent to negative 1. What I do now is raise both sides to p minus 1 by 2. Firstly, p is an odd prime. Assume that p is not even. Okay, we don't care about even primes. Okay, well, we do have to care somewhat. This or p is equal to 2. So suppose that p is not 2, then we do this thing. A square plus 1 is congruent to 0. So this thing is congruent to this thing. But observe that this thing is congruent to a raised to the power p minus 1, which is congruent to 1. Does everyone see that?
Yes.
Okay. Can someone tell me why this implies that p is 1 mod 4? Or more specifically, why p can't be 4 mod 3 mod 4?
because p minus 1 by 2 has to be even, right?
Yes, precisely. This implies that p minus 1 by 2 is even, which in turn implies that p is 1 mod 4. We could have just squared and got the same thing. We could have squared and got the same thing. Oh, right, we could have done the same thing with squares as well. Yes. Thank you, Ayush. So another way to proceed from here is to observe that a raised to the power 4 is congruent to 1 modulo p. Which, now that we have learned orders, I think this is the way I should have covered. But anyways. So this implies that order of p modulo a modulo p divides 4. Therefore, the order P modulo A belongs to the set 1, 2, 4. Observe that it cannot be 1 or 2. Why can't it be 1 or 2? Oh, wait, sorry. Was this much clear, like what we are doing right now? Is this clear? Like what I mean by this?
Yes.
A power
Good.
4 minus 1 is congruent to 0 mod p. So if uh, the order is 1 or 2, then a power 4, wait a second.
Yeah, take your time. Oh, also other people like Ashutosh, Advik, Keshav, Arsh, feel free to speak up.
So because a square is congruent to -1, order can't be 2,
Yes,
and it
precisely.
obviously can't be 1.
Yes, because observe that a square is congruent to -1 modulo p. If the order was 1 or 2, this would imply that a square is congruent to 1 mod p. Do people see that? Okay, wait, I should write it better.
Yes.
Okay, I suppose it's clear. I will still write it. Okay, so this implies that the order of a modulo p is equal to 4. Now we know that the order divides p minus 1. Therefore, 4 divides p minus 1, which implies that p is 1 mod 4. Nice. We have two proofs of the same fact. Okay, anyways, I think we have enough machinery to do this problem now. How tough is the second buffer problem? It's not that tough. Like it's order. It was a 2 club for reference. It was a 2 club. Either way, this problem. Any ideas, people?
You can again take some prime dividing n,
Sure.
and then 2 raised to n minus 1 will be congruent to -1 mod p.
I agree.
By the way, just a
How?
question. Are we allowed to raise to inverses?
What do you mean by? I think you mean by raised to negative integers.
Not negative per se. So basically what I want to do is I assume that n minus 1 is
Yeah.
equal to 2 raised to t times u.
2 raised to the power t times u. Sure.
And then so 2 raised to t times u is congruent to -1. And I want to
Modulo what?
remove the u, modulo p.
Oh, okay. So you want to do this, I suppose.
Yeah, yeah. So can we cancel out the u by raising to the inverse of u because u is odd?
I don't think you can raise to inverses, because see, raising to inverses is like taking roots, taking like square root, cube root, and stuff, and that need not necessarily exist. Like,
No, but inverses would exist mod p, right?
yes,
Or is
but
this
you're
not
not
existing?
multiplying it by an inverse, correct? I
And I'm
mean,
saying
what
raise
was
both sides. I'm saying raise both sides, and then that would in turn get multiplied in the exponent.
okay? What do you want to raise it to?
1 upon u, or the inverse of u mod p.
Okay, what if there does not exist a uth root of -1 in this? I mean, suppose. Oh wait, I think this should be no. This shouldn't be bad. This is bad. Yes, yes. This is not particularly okay. Is u odd? U is odd, right?
Yeah, u is odd.
Then I don't think it should be an issue. But see, in general, you should not do this because, like, -1, like the square root of -1 doesn't exist mod p if p is congruent to 3 mod 4. And similarly, like, you can also give these statements about fourth and next roots. So in general, raising it to like this is not a good idea. Yes, there is. Yes, that is also another good point. There will be many roots of this thing, right? Wait, I forgot who was speaking. Was it Keshav?
Yeah.
Yeah. So -1 raised to the power 1 over u can have many solutions, right? Like you're just asking a raised to the power u congruent to -1. This can have many solutions. More precisely, it will have at most u solutions. So you will be pretty sad after that, I think.
Yeah, makes sense.
Yeah, you won't really be able to control what's going on.
Yeah. So what I got by assuming that it's fine is that the order must be a power of 2, which is something.
Interesting. Interesting. Okay, also people try to use is there a highlighter option in this? Oh cool, that is. Try using this fact which we just proved. Okay, this fact. Try using this fact here. Yes, try applying this thing to this thing. Ah, interesting.
And that directly gives us that P is congruent to 1 not 4.
Yes, that is correct. So I will write that down, I suppose. Wait, should I use a black pen or a colored one? Which one looks cooler? Do you people have any preference in color? I will take that as a no. Oh, someone said something. Use blood red. I don't know how to change the shade. I will just use the red I have. Yes. So we have that P divides 2 raised to the power n minus 1. Sorry, n divides. Stronger statement. N divides 2 raised to the power n minus 1 plus 1. First observation. N is odd. Is this clear why that is true? Like,
Yes.
yeah. So n is odd because if I will just sketch a small thing. If 2 divides n, that implies 2 divides 2 raised to the power n minus 1 plus 1, which in turn implies that n minus 1 is equal to 1. No, what n minus 1 is equal to 0, which implies that n is 1. If so, in this case as well, in this case as well, we get that n is odd only. So, like, we get a contradiction, parity stuff. Wait, what? Am I coping? Okay, I'm not coping. Nice. So we have that n is odd. Now take a prime p that divides n. This implies that p divides 2 raised to the power n minus 1 plus 1. Observe 2 raised to the power n minus 1 plus 1 is equal to a square plus 1 for some a. All I mean by this is the exponent here is even. Is this clear?
Yeah.
Nice. So this gives us that the prime P, sorry, what was this saying? Yes, the prime P is congruent to 1 modulo 4. Is this clear why this is true? Like, this is just applying this lemma we proved earlier. This is clear, right?
Yeah.
Cool. So this holds for all prime P that divide n. So can we conclude that n itself has to be 1 mod 4?
Yeah.
Nice. But as n is 1 mod 4, observe that n minus 1 is divisible by 4. So 2 raised to the power n minus 1 plus 1 is equal to a raised to the power 4 plus 1 for sum a. I suppose this is also clear. Wait, if I'm going too fast or something, you can tell me. I will like recap something if you want.
Can you repeat once
Yes, which part?
from the first P congruent to 1 mod 4?
Okay, sure. Yes. So see, P divides, we got that n is odd, right? Did you get that n is odd?
Yes.
So let n equal 2k plus 1. So we get that P divides 2 raised to the power 2k plus 1, correct?
Yes.
Observe that this is a perfect square. Sure.
Yes.
And this is 1. Now we apply our lemma. If P divides a square plus 1, P is 1 mod 4. We get that P divides a square plus 1. So we conclude that P is 1 mod 4. Is that clear?
Okay. Yes.
Anything else? Anyone? So I suppose this is clear to everyone. Now, so we get that P divides a raised to the power 4 plus 1. Now we derived the result for like 4 being 2. Can you give me a stronger result when it's a to the 4 plus 1?
P will be 1 mod 8.
Yes, the chat people, the idea is that. What? P will be 1 mod 8. True. And why is it that? Why is that so?
The same orders we
Yes.
put. So
No.
a raised to 8 will be congruent to 1 mod p.
Yes, a to the 4 congruent to a raised to the power 8 congruent to 1 mod p. Sure.
And then we get 8 must divide p minus 1 because the other factors are not considered here, right?
Yes.
So p is congruent to 1 mod 8.
Sure. Nice. No, I am skill issuing again. Above order of p mod a is equal to 8. Is this clear to everyone? Like what we just did? Anyone who is not clear with this?
Clear.
Okay, I suppose this is clear to everyone.
Yes.
So what?
Yes, it's clear.
Okay, cool. So this implies that p is congruent to 1 mod 8. Now what you do is you do same exact argument as above, to conclude that n is also 1 mod 8. And then you keep doing this and you get an infinite descent. I like, you will have to write that down in an induction style somehow. I won't go into the details there, but it's not hard to write. Trust. I think it's a bad thing. I should not say trust me in my class, but yeah, what can we do?
Wait, you can't cite infinite descent in a contest.
But you will actually have to show that an infinite descent occurs, right? So like you will have to show something like, assume that n is 1 mod 2 raised to the power t. We show that by induction, we show that it is also 1 mod 2 raised to the power t plus 1 for all this, that blah 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 induction things. So this gives us an infinite descent. That is how you will have to write. Is that clear?
Yeah.
Cool.
By the way, we would have gotten the same thing using the inverse idea that I gave, right? If we weren't running
Yes,
out of
but the
issues.
issue is you would not have gotten 1 here. Like, I mean, wait, where am I? I forgot where I wrote your inverse idea. Yes. So this 2 raised to the power this thing. Why are you sure that this has to be 1?
No,
Like,
it need
if
not be one. Like it can be odd, but then we raise it again, we square it again, right?
okay, and you keep squaring it, so why will it eventually give me a 1?
So okay, so suppose the inverse exists and we aren't running into issues. So
No, I'm saying like, suppose that you get that 2 raised to the power 2 raised to the power t is congruent to, what am I doing in life? Can't write a freaking equivalence sign. Is congruent to k modulo p. What now? Oh, I'll write with a green pen.
no, but how will it be k? It has to be -1 or 1, right?
No, right. Suppose that your u is equal to p minus 1 over 2. Okay. Take a quadratic. Okay, wait. Do you know what a quadratic residue is?
Yeah.
People who don't know what a quadratic residue is, feel free to skip this part. Take a quadratic residue a, then a raised to the power p minus 1 over 2 is congruent to. Okay, take a non-quadratic residue. Sorry, take a non-quadratic residue. You get this thing.
Yeah.
But from here, you can get that 2a is congruent to -1 2 over p minus 1. So if your u was like p minus 1 over 2, you can get a as one of the results.
Yeah.
So do you see why this fails? Like, you can't just square it. It need not just be 1 or 1.
I see. Makes sense.
Yeah, cool. Okay, so do you people want to do another problem on orders, or do you people wish me to introduce primitive roots? Which do you want to do?
Primitive roots.
Okay. Any other votes against primitive roots? Otherwise, I'll just do primitive. Okay, there are some charts. Either of them works. Primitive. Okay, I think primitive roots has the. Yeah, I think primitive roots has the advantage. Sure, we'll do primitive roots. Primitive roots are very fun. You can do very nice stuff with them. Primitive roots. Also, just a very little tangent that I'm going off. We were looking at the equation, this mod p. What if I remove the modulo p condition? Please send those problems after class. Yeah, I'll put the problems in the p set. Don't worry. So what if I remove this? Should use some other pen. What if I remove this modulo p condition? What happens then?
Like roots of unity.
Yes, precisely. You get roots of unity. So if some of you do end up studying higher maths, what you will see is that a raised to the power n congruent to 1 modulo p are actually similar to the pth primitive roots of unity. Like, does everyone know what a primitive root of unity is?
I don't know it.
Okay. Okay, I don't think we should go into this discussion when we haven't even completed the intended things today. I'll get back to this fun part at the end. Yes. Let's just define a primitive root. So, in simple terms, if order of A modulo P is equal to P minus 1, then A is called a primitive root. Primitive root. Can someone tell me why this is interesting? Oh, you don't get into cyclotomic polynomials. You get into roots of unity where you can do weird complex number stuff. You also get into you can look at cyclotomic polynomials modulo P, which also give you very interesting results. In fact, I think I'm not very sure about this, so don't take my word for it. But the proof of Dirichlet's theorem for the case of 1 can be done with cyclotomic polynomials. Yes, that is indeed correct. Who was this? Ayush. When the order is P minus 1, A is called a primitive root modulo P. Yes, A is called a primitive root modulo P. That is correct. What we get is that 1, A raised to the power 1, A raised to the power 2, A raised to the power 3, A raised to the power P minus 1 completes the entire non-zero residue set modulo P. Is the same as 1, 2, 3. Is this equality clear?
Yeah.
Just a second, something is happening. My computer is not working how it should. Okay. Is everyone clear with this equality? Is everyone? Feels like we're going to do something like it. No, you don't have to do as much work as you do in Fermat's little theorem. Just observe that none of these two can be equal. Okay. Suppose
Just two.
what?
Like two can't be same, no?
Yes, exactly. That is precisely the thing. There is these two are not equal. Suppose for some I comma j, we get that a raised to the power, this is congruent to a raised to the power j minus 1, sorry, j modulo p. This would imply that a raised to the power I minus j is congruent to 1 modulo p. Observe, mod I minus j is strictly less than p minus 1. And this gives you a contradiction because you get a smaller order, right? You get something smaller than an order. So everything will be different and you're done. Does that make sense, people?
Yes.
Pretty cool. Other people other than Shiva just say myself back. So remove pen.
No audio.
Wait, am I audible, people? Sorry for
Yes.
that.
Yes, you are.
Okay, nice. Thank you. Sorry for that. Okay, wait, I am not a host. Wait, whoever the host is right now, make me the host, please. Who's the host right now? Ayush Bhargav, can you make me the host? Thank you for that. Is my screen visible? You can claim it also though. Then that imply this one mod P. Oh wait, is this not clear? Should I repeat this? Yes, I should repeat this. Okay. So let me change some conditions. If you get two different INJ of these two which are equal, okay, then is this equation clear to everyone? The one I am circling right now. Horrible circle, horrible circle.
I think that a power j into a power I minus a should be 1 more.
A
So how
power, sorry, I did not get that.
a power j and okay. uh,
What is happening? Wait, is this line visible to everyone? So annoying. Sorry, could you repeat, Anirudh? What were you saying?
yeah. So a power I minus a power j would be a power j into a power I minus j. I minus j in the exponent. So how did we cancel the a power j part?
Oh, okay. So observe a comma p has to be 1. If it is not, then the order can like the order is just not defined for this, right? Because you can never get 1.
Yeah.
Did that make sense to everyone? Why
Yes.
this? Okay. So why is this a necessary condition? That made sense to everyone, I suppose. So this gives you that a raised to the power I minus j is congruent to 1 mod p. But this gives you a number less than p minus 1, which works as the order. So we get a contradiction, and hence this creates the entire residue set.
But a power j might be congruent to something other than 1 mod p, right?
No, right? See, okay, I'll write it. I'll write the steps. So you get that a raised to the power j times a raised to the power I minus j minus 1 congruent to 0 modulo p. Observe that we are working modulo p. Therefore, at least one of this guy, or this guy has to be 0. At least one of these is 0, right?
Yeah.
So then what we get is
I got it.
a
Got
raised to the power j is not congruent to 0 because of this condition. Is that clear to everyone?
Yes.
Others as well. Okay, I suppose it is clear. So this gives us a contradiction. Therefore, no two of them are equal and none of them are 0. That is why we get every number from 1 to v minus 1. Cool. So we'll have our first problem of the day. Compute 1 raised to the power n, 2 raised to the power n, 3 raised to the power n, p minus 1 raised to the power n, modulo p. Oh, also, how are the buffer problems going? If anyone wants another buffer problem, I have, feel free to ask. Are people were done with the old buffer problems I gave?
Yeah, I finished them.
Are you done with the 20, 12, and 6?
No.
Oh, okay. Try that. If you have seen this. If you haven't seen this, like continue. I have done 1 and 2 on this. Oh, good. Can't do IMOSL. You can press. Though I think that is like a little difficult. I should not have given the N6. Could you please share the 3 buffer problems again? Yes, I will show you the buffer. Has everyone noted down this problem?
Yeah.
Sure, I'll take that as a yes. This is the first buffer problem we had. This is not that difficult a problem. Pretty easy, I would say. Did you get it? Who is this? Vairagya. Did you get this? Okay. This is our second buffer problem. Are you done take? Oh, this is 2 raised to, okay, shit. Okay, this is so horrible of me. Wait. People, for whoever they were, this is 2 raised to the power m. Sorry. 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 Yeah. So this is our second buffer problem.
Wait, the thing is also provable for 2m.
2m, it's just easy, right? Like, take any
Yeah.
even n and it just works.
Yeah.
Exactly. It's pretty trivial for 2m. 2 raised to the power m is also not that hard, but it's a little more work. So try this. Try 2 raised to the power m. It's better. Plus. So I should not have copied the problem. Hopefully there aren't typos in the third one. Wait, does anyone know where is the third buffer problem? I can't seem. Oh, wait. Okay, I just told you the name of the last one. Vairagya, the last thing is IMOSL 2012 and 6. It's a little difficult, but can be done with orders and similar ideas. Yes, people. So, any ideas for this thing?
Can we write this as a GP or something using primitive root?
Yes, that is precisely the idea. Uh,
If n is odd, then it is 0 mode.
yes. No, that is not true. I don't think that is true. Is that true? Oh yeah, that is true. Yes. Odd and it is 0 mod. You can give a stronger statement though. You can give a stronger statement. Observe that the set is the same as the set for a primitive root g. So summation I raised to the power n, I equals 1 to p minus 1. Oh, also everyone is comfortable with the summation notation, right?
Yeah.
G raised to the power I raised to the power n, which also turns out to be congruent to, okay, this is math. Yeah. Now we need to make two cases actually. You get 1 plus 1 if p minus 1 divides n. Can someone tell me why this is true? Why is this statement true?
Because then you can like transform the thing to say g raised to p minus 1 raised to something.
Yes, precisely. So in this case, you just get summation g raised to the power p minus 1 raised to the power I into k, where k is equal to n divided by p minus 1. And this is obviously just congruent to summation 1 mod p. Is this clear to everyone? Should I repeat this, like go over it in more detail, something? This is also from Mon, right? This is a general thing, like repeat it. Yes, I will. This is a very general thing. Like this problem is done everywhere where order primitive roots are done. Okay, so case 1. I will write it better. Case 1. P minus 1 divides n. Suppose that n is equal to p minus 1 into k. So g summation. By this summation, I am not putting the upper and lower bounds for this. It's understood that it's from I to p minus 1. Sorry, not m. N is congruent to summation g raised to the power I into n, which is congruent to summation g raised to the power I into p minus 1 into k, which is congruent to summation g raised to the power p minus 1 raised to the power I times k. Observe that as g is a primitive root, or even otherwise, g raised to the power p minus 1 uh, will always just be 1 mod p. Okay, this is congruent to summation 1 raised to the power ik, which is just 1 plus, I'll put the bounds here. We have p minus 1 total numbers from 1 to p minus 1. 1, negative 1. Is this clear, people?
Yeah.
Yes. Anil and Alex as well.
Yes.
Cool. Case 2. P minus 1 does not divide in. So observe that g raised to the power 1 plus g raised 1, sorry, I'm dumb. G raised to the power n plus g raised to the power 2n, g raised to the power p minus 1 n is the same as 1 plus g raised to the power n, g raised to the power p minus 2 times n. I've done what I've done is just write this term is 1. Do you see this, everyone?
Yeah.
Cool. Now this forms a geometric progression. So apply the GP formula. G raised to the power number of common ratio raised to the power number of terms, right? If I'm not wrong. So first question, why is the denominator well defined? Or equivalently, why is this not equal to 0? Not
Because
congruent to 0.
we're considering the case where p minus 1 does not divide it. And so this limit is
Indeed.
0.
Yes, that is correct. So was that clear to everyone other than Keshav? Everyone else, was that clear? As
Yes.
G, great. So additionally, observe that G raised to the power n times p minus 1, this quantity will be congruent to 1. Do you see that? I'll just write it 1 minus 1 G to the n minus 1, which is congruent to 0. Yay! We have proven our first problem using primitive roots. Therefore, we conclude summation I equaling 1 to p minus 1 of I raised to the power n is congruent to negative 1 if p minus 1 divides n and 0 otherwise.
By the way,
Yeah.
how do we know that every prime P has a primitive root?
Excellent question. I was hoping no one asked this. So yeah, I will tell you another statement. What was the statement I wanted to tell you? Yes. A primitive root will give a more general definition. Now, the set g raised to the power 1, g square, g cube, g raised to the power phi of n is the set of, I should write this, is the set of numbers mod n co-prime to n. This is the definition for a general n. Like this is the definition of a primitive root for a general n. Is this clear, people? Like, does this make sense, or like should I like write a bit more of this?
I think it makes sense.
Nice. Other people.
Yeah, it makes sense.
Cool. It is somewhat like Euler's theorem, I would agree, but it's not really Euler's theorem. Okay, so now I will give you a theorem which we will not prove. Theorem. A primitive root exists modulo n if and only if n is of the form 2 p raised to the power k 2 into p raised to the power k. These are the only cases when a primitive root exists. So either I can give you the sketch of this proof, or we can do another problem on primitive roots. What do you want?
Can we discuss number of primitive roots?
The number of primitive roots. Yeah, sure. That won't be an issue. So I suppose people, yeah, this is a well-known theorem. You can look, you can try to prove this. It's not that hard. Other than the case of P, I think P is the hardest case in this. Like, I think this is the hardest case. Either way. So now we will do another problem. Show that number of, okay, this means number of primitive roots mod P is P minus 1. Sorry, phi of P minus 1. Yes. This will be the last problem for the day. Any ideas? Any ideas that you get, feel free to say it. Also, for the people who are interested in generalizing this, when you replace P with N, you get phi of N instead, where N is of this form.
Wait, by
You get
the
phi of
way,
Yeah.
here, doesn't this problem imply a case of the previous one?
This thing.
Yeah,
Which problem?
meaning if a primitive root exists more than n is of the form 2p to the power k and 2 times p to the power k. So if
Why does that imply it? Like, why does this problem imply this problem?
no, not the whole problem, but a part of it, right? Because this shows that every prime p must have a primitive root, right?
Oh no, we are assuming. Okay, wait. Sorry. Thank you for pointing it out. Show that this is this given at least one primitive root. You are given one primitive root, primitive. Yes. Primitive root. You're given one primitive root and you want to show that phi of p exists. You are not really. Sorry for that. That was unclear. Thank you for pointing it out, Akshay. Can you read the problem? My screen is having problem. Yes. You want to show that you are given one primitive root modulo p. You want to show that there are p primitive one primitive roots modulo p. Any ideas, people? Any ideas at all? Okay, in case you want a hint, tell me. If you want a hint.
Do we form some sort of cycle between all co-prime numbers modulo or all co-prime numbers to be?
Can't hear. Wait, am I? You
Now you are audible.
sort of cycle between this. Interesting. Wait, I wasn't audible
So, okay,
before.
we know that for like a second or so.
Sorry, hello? Yeah,
Yeah,
go
now
on.
you're on. Yeah. So we know that a primitive root must be co-prime to P, right?
Go on, go on.
So do we
Yes, I
form like
agree.
a
I think,
so
I mean,
from
everything is co-prime P. Yes, continue. Keshav,
so do
am
we
I
like form some sort of cycle using exponents?
using
Like
what?
this primitive root, so like this primitive root will imply the existence of some other primitive root, and you jump between those or something like that.
Yes, that is indeed a good. We know that the set, uh, I will start with one. This set G to the P minus 2 is same as the set 1 to P minus 1. Correct. So
Yeah.
this set contains the other primitive roots as well. That is the key idea. Like it must also contain the. So
Okay, so is it like you in the set 1 comma g squared to the power and till g to the power p minus 2, any number in this set which is coprime to p minus 1 would just be a primitive root, right?
precisely, that is indeed correct, Akshay. So let's give others like 2 minutes to think, and then I'll say that. In the meantime, we can try the buffer problems, or I can give you a problems on primitive roots if you want.
So can you prove that all of the primitive roots are uh, meaning what I'm trying to say is if you are given, let's say, a smallest primitive root of p, then okay, sorry, this is stupid.
Ah, yes. Like the notion of smallest is also pretty weird in these things. Like it's pretty weird, like defining a notion of smallest. You will have to like if you're talking about. Okay, sorry, that isn't really relevant though. Okay, in case some people are interested, we can talk a little bit about what.
I can't hear your voice.
Wait, am I not audible?
You are audible.
Ah, Britaji, I think it is some issue on your side then. You should check
Okay.
your speakers and stuff.
I think
By the way, here we just take B to be co-prime to P minus 1, right?
Yes, that
Uh,
works precisely. That works.
yeah.
Okay, so claim if b comma p minus 1 is 1, then g to the b is also a primitive root. Root. Cool. Anyone interested in proving this? Or anyone who wants me to prove this? Or is this clear? Feel free to DM me if you want me to like say this, prove this thing. I think I should just prove it. It does not take too long. Okay. So how do we show that something is a primitive root? Tell me this. How do we prove that something is a primitive root?
Nothing smaller than p minus 1 can be the exponent.
Yes, the order is p minus 1. We want that order modulo p g raised to the power b is equal to p minus 1. Yes, we do for the sake of contradiction. Say, assume that order p mod gb, order just gb mod p is some c. That implies g raised to the power bc is congruent to 1 modulo p. But that implies that p minus 1, sorry, I will write the order of g mod p divides bc, which is the same as saying that p minus 1 divides bc. As p minus 1 and b are co-prime, we get that p minus 1 divides c. But that's a contradiction. Okay, no, it's not a contradiction. We didn't start for a contradiction. That implies that g raised, wait, what do I want to say? I'm very sorry. This simply implies that the order of p, order of g raised to the power b modulo p is p minus 1, which is what we wanted. So we are done. Did that make sense? And I'm sorry for fumbling in between. Did that make sense?
Yeah.
Yes, people other than Keshav, did it make sense?
Yes.
Good, thank you. Okay, I'll end the class with giving you 2 problems.
By the way, can you also discuss, as you were discussing in the start, the connection between.
Oh yes, I'll do that after I close the recording. We don't want yapping to be there in the recording, right? So, problem. Suppose G1, G2, dot dot dot, G raised to the power, G phi p minus 1 are the primitive roots mod p. Then summation g sub I equaling 1 to phi p minus 1 is congruent to 1 mod p, while the product gi I congruent to 1 phi p minus 1 is congruent to mu p minus 1 mod p. Sir, are you free to do G solve on combi? Yeah, probably. I'm usually free. Try DMing me. I'll probably come. Or call you to a G solve. We are already doing. Yeah. Either way. Does everyone know what the new function is? The mu function, sorry. Mu of n. Do you people know how it's defined?
Yeah.
Good. Does everyone know how it's
I
defined?
don't know.
Okay, sure. I'll just define that. Mu of n, where mu of n is 0 if n is not square p. And minus 1 raised to the power k when n is square p and k is the number of primes dividing n. Okay, I'll just do some examples, I suppose. So mu of 4 is 0 as, what am I doing? As 4 is not square free, like 4 divides 4. Mu of, let's see, 18 is also equal to 0 as 9 divides 18, while mu of 30 is equal to negative 1 raised to the power 3, which is negative 1, as 30 is equal to 2 into 3 into. Are people clear with the definition of the mu function? Or wait, is it not clear? Should I go over this again? Am I audible?
Yeah, you are.
Oh, thank you. Was this clear or was this not clear? Okay, Anirudh says it is. Other people. Okay, wait. Do you people know what square free means? Do you people know what square free means?
Yes, it does not have a square.
What? Yeah, it is not divisible by any square, precisely. This is the first condition. So if it is not square free, that is a perfect square divides it. So it will be 0 and it will be minus 1 raised to the power k otherwise. I hope I'm not messing this spell. Like, I'm very sure I'm not messing this up. Yeah. So this comes under the more general category of arithmetic functions. Sorry, number theoretic functions, not arithmetic functions, which is covered in Mont chapter 3. It does a lot of fun stuff there. So do check that out. And this was the end of our class. Thank you for attending. Stop recording. Wait, did I stop? Okay, I haven't stopped recording.